Good day everyone. Welcome to another video of this lecture series on machine learning. So in this particular video, we will continue the discussion of the last lecture, that is gradient descent. So we said that this particular algorithm is used to find the optimal values of theta such that j theta is minimum. J theta is our cost. And we said that how we can do it. Our algorithm is for we will update j is equal to 0 to n, this theta j, and this theta j will be is equal to theta j minus learning rate into summation I running from 1 to m h of theta xi minus yi into xij. So this is how we will update theta j, and we have to do this till j theta is not changing significantly. Okay, you can easily write the code for this in Python programming language, and I will also be providing the basic program to do this in Python, but you should also try on your own. Okay, however, what is the aim of this particular video is that we will write these updates in matrix format, because we already know that we have x is our input matrix, y is our output matrix, and we have to find theta, the optimal theta such that our hypothesis function becomes same as our output. Okay, and initially we will give some initial random values to thetas. Okay, now let me see how we can write it in matrix format. So let's do one thing. So if I write the same equation in matrix format, it will be like this. Theta is now our matrix. So you know that theta is equal to theta 0, theta 1, dash 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 up to theta n. Okay, so it is in matrix. In matrix it will be equal to theta minus alpha times j of theta with theta. So this is matrix and this is also matrix. Now let us see how we can find the differentiation of a matrix with respect to a matrix. Okay, so basically, so this is not a matrix, this one, j theta is our cost, so it is a single entity. Okay, and we are finding the differentiation of this quantity with respect to a matrix. Let's first see how to find the differentiation of a matrix of a quantity with respect to a matrix. So that will also be a matrix where we will have differentiation of this theta with respect to the first element of this matrix. What is the first element? Theta 0 with respect to theta 0. Differentiation of this matrix with respect to theta 1. Differentiation of this particular quantity with respect to theta n. Okay, we already know that differentiation of theta j theta with respect to theta j. So here it is 0, but theta j, if I write, it is equal to summation I running from 1 to m j of xi minus yi into xij. J here is 0. Okay, this will be the first quantity. The second will be summation I running from 1 to m j of theta xi minus yi into, sorry, it is not j of theta, it is h of theta, sorry, h, hypothesis, okay, into xi1. And we have to do the same thing up to summation I running from 1 to m h of theta xi minus yi into xi n. Okay, fine. So let me write this again, this equation. So it is equal to, we can write it in this particular format. So let's first see what is this h of theta xi minus yi. So what is this? What is this h of theta xi minus yi? It is basically h of theta xi will be theta 0 plus theta 1 xi1 plus theta 2 xi2 plus dash 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 theta n xin, okay, minus yi. And we have written summation I running from 1 to m. Okay, so this I is changing, it is 0, it is first 0, I is first 1, then I is 2, then I is 3. Similarly it is here as well. And in matrix format it is written like this. This particular is written as x dot theta minus y. So this entire quantity can be written like this, x dot theta minus y. Because what is our x? X is an input matrix that contains all examples. Okay, here also we have to do all the examples, and we have to multiply all those examples with feature vector, with these parameters minus the output, the actual output. Okay, and to this quantity the multiplication is this xi0. So it is saying 0 remains same, I, 0th feature of first example, 0th feature of second example, 0th feature of third example. So what was our x? So x was like this. The first row, so these were its rows. The first row is the first example. The second row is the second example. So every row in this matrix is an example. For example, ith row means ith example. And every column represents the, let's suppose jth column represents the jth features of all the examples. So that means the first row, this row, the first column represents the first, this represents the first feature of all the examples. Or I can say that this is x10, this is x20 dash 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 xm0. Second one will be x11, x12, sorry, x21 dash 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 xm1. So when we have a multiplication like this here, xi0, it will be same as multiplying with one particular column. Because it is saying multiplication means multiplying with one column. But we cannot multiply one column to this. Because to a matrix, if the first is matrix, second should be a row. Okay, second cannot be a column. So that means we have to bring this x at the beginning. Okay, so for x0, for first one, we have to multiply it with the first row, sorry, first column. Okay, if it was xi1, then we have to multiply it with the second column, likewise. Okay, so that means this particular quantity, so this thing, the thing that we were doing, so we were multiplying these. So this can be said as first column, this as second column, this as third column, and this particular quantity is same for all. You can see it is same in all. So this will remain in all these we can say all these elements, this particular part, but the second part is changing, this part. Okay, I can write this particular thing, this entire thing in this particular format. I will write it like this: x transpose x theta minus y. Okay, what I am saying that I am writing this particular quantity in this particular format. Why? I will show you. So what is x transpose? X transpose will be the transpose of this. So the transpose of this will contain, now in x transpose, every row is this column of x and every column is this row. So if I am doing like this, x transpose dot this, it will say take the first row of this. So that what is the first row? First row is like this, xi0. Okay, and multiply it with x theta minus 1. So what was x theta minus 1? X theta minus 1 was this particular quantity. Then this will be the first element of this result. The second element will be x. So I am now writing it in matrix. I am writing it I0, but you should understand it is the first row of x transpose. xi1 x theta minus y dash 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 like this. So it will be same as this one. These two are same, this one and this one. So this means that j of theta, differentiation of j of theta with respect to theta, it is equal to, in matrix format, x transpose into x theta minus y. You can also see it from here. For example, if you want to cross check whether I am correct or not. So what is this? What is the dimension of this matrix? N plus 1 cross 1. What is the dimension of this? N plus 1 cross 1. So it is a constant quantity, we don't care. Now we have to find the dimension of this. What should be the dimension of this? It should be again n plus 1 cross 1. Why? Because two matrices can be subtracted only if their dimensions are same. Okay, let's cross check whether the dimensions are coming n plus 1 cross 1. Okay, so what is the dimension of x transpose? So dimension of x transpose is n plus 1 cross m. Why n plus 1 cross m? Because the dimension of x is m cross n plus 1. Okay, now let's see what is the dimension of this quantity, because we have to multiply these two. So what is the dimension of x? M cross n plus 1. What is the dimension of theta? Dimension of theta is n plus 1 cross m cross 1. Okay, so what will be the dimension of x theta? It will be m cross 1. And we already know y is also m cross 1. So the dimension of this particular quantity will be m cross 1. And if we multiply these two together, the dimension, final dimensions will be n plus 1 cross 1. So you can cross verify the dimension that we needed here. It is coming same as here. Okay, so in matrix format, I can write it. The update rule will be theta is equal to theta minus alpha times x transpose x theta minus y. Okay, this will be the update rule. We don't have to update each theta separately. So here in the iterative model, so this was our iterative model. Let me show you. So this was our iterative model. So we were updating each theta in an iteration. Okay, but here we are using matrix format and we are doing the same using a single matrix equation. So we have to repeat this. We have to repeat this again and again till we reach to the minimum of j theta. Okay, and you can see the one thing in this particular gradient descent model, it is also called a batch gradient descent. Why it is called a batch gradient descent? You can see from here, both in the iteration or in the matrix format. You can see, for example, let's take the matrix format. If we have to update theta, we need the entire data set. So we require entire data set because we are using the entire x here. X is using, we are using it in complete. So we require entire data set for each updation. So that is why it is also called a batch gradient descent. We are using the batch of data, complete batch of data to do one updation. Or here also in the iteration model, you can see, so this was our iteration model. So we are doing theta j is equal to theta j minus alpha times summation I running from 1 to m. So that means we are using the entire, all the data I to m for doing one updation. So it is called batch gradient descent. And the disadvantage of this is that it will be handy. It will be handy in a sense that we require entire data for doing each updation. Okay, and it will also take some time to reach to the optimal value of theta. So we have discussed this batch gradient both as an iterative approach and as a matrix approach. Okay, so this was about batch gradient descent. Now there are other gradient descent algorithms as well. For example, there is another one that is called stochastic gradient descent. So what was batch gradient descent doing? It was doing the updates, but for every update it was using the entire data set. So that was its disadvantage as well. However, in stochastic gradient descent, we are using each training example separately. We are not using the entire data set. Okay, a batch stochastic also we can say random. Let me show you how we use it. So let me write it is stochastic gradient descent. Okay, so our update rule was like this: theta j will be is equal to theta j minus alpha times summation I running from 1 to m h of theta xi minus yi into xij. So this was our update rule in batch gradient descent. But in stochastic gradient descent, what we are doing, from the training set we will take one example. So here we were using all the examples from I to m. But what we are going to do, we will change it like this: theta will be equal to theta j is equal to theta j minus alpha times h of theta xi minus yi into xij. So here this I, so here we are taking only how many examples? One example. Here we were changing from I equal to 1 to m. So this I is chosen randomly. That means we will take any example from the data set. By taking that example means we will take it as input. We will take it as input and compute h of theta. We will find it as output in the data set. We will do the subtraction, okay, and then we will multiply it with the ith feature of this particular jth feature of this particular example, and we will update the theta of j. So you can see that in batch gradient descent, entire data set was used to update theta j, but here one training example at a time is used to update theta j. So we can say the theta j, updated theta j values are getting very quickly because only one example is used to update theta j, but here it was using entire data set to compute, to make updates on the theta. So let me write the differences here: batch and stochastic. So this batch was using entire data set, to update theta. It uses examples randomly, one example at a time. So each updation will be slow, but here each updation will be fast. Okay, that is the main difference here. Every update is getting after some time, but it is very fast. But one advantage of batch is that since it is using the entire data set, each time the updated j theta will be more close to optimal. And this one will be less close to optimal on each updation. So that is the only difference. Fine. So this was about the gradient descent, and it's two different types. One is batch gradient descent and another is stochastic gradient descent. We can combine this stochastic and batch together. How we can combine these two is that we can have a mini batch gradient descent. What does that mean? Mini batch gradient descent. Instead of taking the entire data set, we will take one subset of entire data set, or we can say we will divide this data set, let's suppose, into k subsets, and then do the updates to theta using each subset randomly. Okay, that is the mini batch gradient descent. So it is the combination of batch and stochastic. I will show the examples of Python, how we can do the stochastic in Python, or how we can do the batch gradient descent. Fine. So here I will stop this particular video, and in the next video we will see how we can directly find the optimal theta directly without doing these iterations and other things. So here we have to do iterations repeatedly, both in the matrix format and the iterative approach. We have to do the iterations repeatedly till we reach to the j theta. But in the next lecture we will see in a single step we will find a theta that will give us the minimum j theta, or we will find the theta at which this j theta is minimum. Okay, so with this I will stop this particular video, but I will summarize what we have already discussed. We discussed that for mapping data, one algorithm is, or we can say one machine algorithm is, linear regression, and this linear regression tries to find the optimal values of thetas so that it will find the proper hypothesis function. And this hypothesis function, for finding this proper theta, we have to decrease mean square error. And the main method of decreasing the mean square error is gradient descent. Okay, so this completes the discussion about linear regression and gradient descent, and in the next lecture we will see how we can find this optimal directly without doing these iterations. That is also called normal equations, normal equation format. So in the next lecture we will start discussing about the normal equations. So let's meet in the next lecture. Till then, goodbye.